Hello everyone, welcome to Coders Camp. So we are today at the 24th day of April LeetCode challenge, and the problem we are going to cover today is critical connections in a network. So given input here is an integer value n and the connection which represent the edges between each node in a directed graph. And we have to return the list that is pointing at the critical connections in the given graph. So let's first understand this problem with an example. So here is our given input graph and the connections. So here in input n is equal to 4 represent the number of nodes in the given network, and the connections array or array list is representing the connection between each nodes. So before going to this solution, let us understand what is a critical connection in a network. For example, consider this graph 1 and 2 connected with one edge. So if suppose we are trying to remove this edge from this graph is disconnected where you cannot traverse from one point to other. So this edge is an important or critical edge in this graph. If suppose the graph is same like this, and if you are trying to remove the same edge again, in this case this edge is not critical because you can still connect the graph throughout and travel from 1 to 2 or 4 to 2, etc. You don't have to depend on that particular edge to travel through all the nodes. So that is actually called the critical edge in a network. So now coming to our example. So here, if you are trying to remove this edge between 1 and 2, the graph is still connected. You don't have any edges that depend on this edge to travel through the graph. You can still start from 0 and travel to 2 and then 3 and then 1. Suppose if we are trying to remove this edge from 1 and 0, again this graph is connected. You can travel from 3 to 2 to 0. So now we are trying to remove this connection 1 and 3. In this case, the graph is disconnected. You can travel from 0 to 2 to 1, but you cannot reach 3 from any of these nodes because the graph is disconnected. So this edge is a critical edge. So that is what we are returning 1, 3 is the critical edge in this network. So how are we going to approach this? So the first approach we are going to go through is brute force. So in brute force approach, we are going to perform DFS for this given graph. So hope you are all understanding what is DFS already. So we are going to perform DFS by removing each edge. For example, the first connection or first edge is going to be 0, 1. So first we are going to remove this connection 0, 1 and try to do a DFS traversal starting from 0 to 3. And we are going to check whether we can visit all the nodes in the given graph. That is, we have n is equal to 4. So every time if we visit all the nodes, then we did not cross our critical connection. So now starting from 0, 1, we removed 0, 1. If you perform DFS, in that case, our DFS is going to start from 0 and then go to 2 and then go to 1 and then go to 3. So it is going to give us 0, 2, 1 and 3. So now this is actually traveled all 4 nodes. So now moving on to our second connection, that is 1, 2. So if we are trying to remove 1, 2, again DFS is going to traverse starting from 3, 1, 0 and 2. Again it has visited all 4 nodes. So now moving on to 2, 0. If we are removing the connection 2, 0, again we are able to traverse all 4 nodes starting from 3, 1, 2 and 0. So now moving on to the next edge 1, 3. If we are removing the edge 1, 3, we cannot travel all 4 nodes. That is, if we are starting from 0, then the nodes we can travel going to be 0, 1 and 2. Or if we are starting from the edge 3, then we can traverse only 3. We cannot traverse all 4 nodes at once. So this means if we are removing this connection, we couldn't travel all 4 nodes given in the input, which is actually the critical connection. Then we are going to return that as the result. So now the time complexity of this algorithm is going to be, we are going to build this solution based on DFS. So any DFS will have big O of vertices plus edges time complexity, and we are going to perform DFS for every node, that is for every connection given. So that is going to be again the number of edges. So it is actually going to be VE plus E square, which is similar to an N square algorithm time. So the optimal solution is to perform this in N time complexity, linear time, that is big O of V plus E. So how are we going to do that? So we are going to get the help of Tarjan's algorithm in order to find the critical connections in a network. So that is going to take big O of V plus E time complexity, but this is not something we can come up in a 45 minutes pressured interview. So let me take this as an opportunity to learn a new algorithm today, not in the perspective of an interview. So let's get started. So before entering into the actual logic of the algorithm, let us understand few terms and thought process in order to go for a better understanding of this solution. So let's first start with understanding the term strongly connected component. So strongly connected component in a graph is nothing but a subgraph of a given graph where all the components are connected to each other. So consider this graph as an example. Here if you see 1, 2, 0 is a subgraph that has all nodes connected to each other. That is, you can travel every node from each node. The same way 4, 5, 6 is again a subgraph which has all connected nodes together. So these two are said to be the strongest connected component. Also 3 is individually a strongest connected component. So here the edges connected between these strongest connected component cannot be a critical edge. I'll explain that why in few minutes. Also here 3 is a separate node. So if you understand the nodes in between one strongly connected component and another strongly connected component is connected by a critical edge. So these edges are going to be our output. So how are we saying the edges inside strongly connected components are not critical edges and the edges connecting them are critical edges? So we are going to understand that. So here in this graph, if suppose we are trying to delete the edge 1 to 2, then still this graph is connected. You can travel from each other node. Same way if we are trying to remove the connection from 2 to 0 or 3 to 0 or 1 to 3, still the graph is connected, which actually means this graph is strongly connected component. So this how this is strongly connected because it is having a cycle. So we can simply say any subgraph or graph which is having a cycle will be the strongest connected component and no edges will be a critically connected network here. So even if you delete any of the edges here, your graph is still connected. The same way consider this graph. If you are trying to delete any edges from this graph, for example 0 to 2 or 1 to 2, 1 to 0 or 0 to 3, deleting these edges will result in separating the graph or disconnecting the graph into two, which means again this is a critical edge. So this graph clearly does not have a cycle. So any graph which does not have a cycle where each edge in that graph will be a critical edge. So consider the same graph in this format, that is it is connected this way and it doesn't have any cycle. So if you're trying to remove each edge, then that edge is a critical edge. So the overall idea of Tarjan's algorithm is that if it finds any graph which has a cycle, which means the edges inside that graph is not critical edges. The same way, the edges does not have any cycle, then these are the edges that are said to be critical edges. So this is the overall idea, and let's see how are we going to implement this using Tarjan's algorithm. So to implement Tarjan's algorithm, we are going to assign or label each node in the graph with two variables. The first one is ID and the second one is low. So ID is nothing but an integer value where we are going to assign every time whenever we visit the node for the first time. So if we are starting to traverse this graph from the node 1, then it is going to have the ID 0 because this is the first node we are visiting here. And if we are visiting the second node 0, then the ID is going to be 1. And the same way if we are visiting third time or as the third node, then the ID is going to be 3. And if we are visiting 3 and it is going to be the fourth node we are visiting, then the ID is going to be 4, and same way it is going to assign each node an ID. So sometimes this ID can be referred as disk in proper Tarjan's algorithm and something else in different implementation. So we are going to refer that as ID here. So the next term is low. So low is nothing but a rank or the lowest node you can possibly visit in the forward direction. So for example, if we are traversing this first node, node 1, the ID is going to be 0. So the next variable is low. So low is again pointing at an ID. It can minimum possibly visit in forward direction. So starting at our node 1, the ID for node 1 is 0, and here the lowest possible node it can visit is again having the ID 0. That is, if we are at node 1, if you have only the node 1 and we did not move forward to any other neighboring node, in that case the lowest possible node it can visit is the same node, that is 1 itself. In that case the ID of 1 is going to be 0. So moving forward, if we are moving to 0, that is the next node, its ID is going to be 1, and the lowest possible node it can visit is itself. So we are going to put 1 again. And if we are moving to the node 2, and the ID of the node 2 is 2 because we are visiting it for the first time, and the low of this node is going to be 2 because the only minimum possible node it can visit is 2 only, because it cannot move backward. From 2 you cannot visit back to 1, from 1 you cannot visit back to 2. Only possible thing is it can move forward. So you can ask, 0 can move forward to 2 as the node 2 is the future node, but here low is going to have the minimum value or minimum rank it can hold. So considering 1 and 2, the minimum rank or ID it can hold is 1 only. So hope you're understanding. So we are going to fill these two values to all the nodes in order to find the critical edges. So Tarjan's algorithm is actually built to find the number of strongly connected components. And we are going to continue to identify the edges which is connecting the strongest connecting components, and those are the critical edges we need to return. So let's start filling the values ID and low for each node in order to see how we are finding the critical edges. So let's start having the value of ID 0, since we are visiting the node 1 as the first node, and its low value is going to be 0 again, because moving forward 1 will be having the higher ID value, so it can hold the lowest value. So now we are moving to the second node, which is 0, which is going to have the ID of 1, and the lowest possible node it can visit here is 1 only. So here this 1 is not the node value but the ID. If it is confusing, you can even assign the values of A, B, C inside it. So these numbers are nothing but IDs of each node, not the actual values of each node. Here values doesn't have any role. So now we are moving to the next node 2. So here we are going to assign the value 2 as this is the third node we are visiting, and it is going to hold the low value of 2 only because it can move forward, cannot move backward. So far the forward value is going to be 2. So since it is going to be a recursive algorithm, we are going to put all the nodes value in stack, and one by one we are going to reverse iterate it as we remove the values from the stack. So now from 2 you cannot go backward, but you can move forward. So if you move forward from 2 you can visit 0 because it is a cycled graph. So since it is visiting 0, the lowest possible value you can visit from 2 is going to change or update to 0, because it can move forward and visit the node 0 and then again move forward and visit the node 1, again come back to 2, since it has a cycle. So in this cycle the possible nodes you can visit from 2 is going to be 0 and 1. Out of 0 and 1, which ID is the smallest? 0. So we are going to put or update 0 here. So once we pull that back from the stack, the next node available in the stack is going to be 1. So we are coming to 1. As we move to 2 and then from 2 to 0, we can visit 0 also from 1. So in that case, the ID at 1 is also going to become 0. So far we have completed the first strongly connected component where all the low values are 0, because in this cycle, the lowest possible node it can visit from each node is going to be 0. Moving on to our next node, which is 3, its ID is going to be 4 because this is the fourth node we are visiting in this graph. So now it's time to fill the low value. So if you see, it can only move forward. If it is moving forward, it is having the nodes 4, 5 or 6. Definitely the ID of 4 is going to be higher. So possibly the lowest graph it can visit here is going to be 4 only. So now moving on to the node 4, here the ID of node 4 is going to be 5 because this is the fifth node we are visiting, and the lowest possible value or node it can visit from this point is going to be 5 again. And moving to the next value 6, we are going to update its ID as 6, and the lowest possible ID node it can visit from 6 itself is 6. And here moving on to 5, so the ID is going to be 7, so it is again going to visit the same node itself, so 7. So here after visiting 5, we are going to explore its option, whether what are the possible nodes it can further connect with. So in this case, it has already connected with 6, but it cannot go backward. So the next available node or neighboring node to 5 is 4. So we can possibly visit 4 from 5. So the ID of 4 is going to be 5. So this is what we are going to update as the low of 5, because from 5 you can visit the node 4 whose ID is 5. So we are going to update the low of 5 is 5, because the ID of 4 is 5. So we can visit 4 from 5, which is the lowest possible node we can visit from the node 5 with ID 7. So hope these numbers are not confusing. If it is confusing, you can try this by changing the values to A, B, C, D. So now again we are removing 5 from the stack as this is recursive solution. So moving on to the node 6 whose ID is also 6. So in this case, the possible node you can visit forward from 6 is 4, whose ID is 5, which is the lowest you can visit. So you can put 5 here as well. And now we have finished. Moving to 4, again you can visit the minimum possible value here is 4. So if you see in this cycle, all low values become 5, because the lowest possible node you can visit within a cycle is the lowest one in the cycle itself. So yes, we have updated all nodes ID and low. So if you observe the values, here everything is having the node value 0, and here everything is having the node value 5. So there is a difference between these nodes, that is from 4 to all these nodes, also from 0 to all these nodes. In this case, from this to this node there is a critical connection, and from this to this node again there is a critical connection. So we are going to assign the values and compare it. If there is a difference in the low value and the ID, then it is actually having a critical connection. Then we are going to add that connection to our result. So hope you're understanding this solution, and I made it simple. And this is going to run in big O of v plus e time complexity, and as we are going to use a memory to save this ID and low, it is going to take big O of n, where n is the number of vertices given, space complexity. So you can implement this using hash map or arrays or however you want. There are a lot of implementations in internet, so we are going to see today an array implementation of this. Let's go to code now. So yes, I'm gonna declare two array, which is ID and low, and a variable time, which is gonna iterate every time we are going to visit the node for the first time. So this will be the value for both ID and low for the first time when we visit the node, and a result integer array list. So let all this be a global variable because we are going to add DFS function. And one more thing, list of graph. So this is going to hold the adjacent nodes of the given node. For example, in this graph, if 1 is the node, then G is going to hold all 2, 0 and 3. So if suppose 0 is the node, then G is going to hold 2 and 1 because these are the connected nodes to 0. So now I'm going to initialize my variables. So here we are assigning our ID array with -1 so that we'll identify which nodes are visited or not visited. So if we visited, we are going to assign the ID to each node, so that if it is not -1, which means we have already visited the node. So let's fill our array G with its adjacent connected nodes first. So for that, I'm going to initialize a new array list for every node. So yes, we have taken the connections, that is our input list. So each connection we are going to take, if suppose the connection is 1 comma 3, then we are going to assign for the node 1, the 3 is the connected node, and the same way for 3, 1 is the connected node. So we are going to assign each node its connection. So we are done with that, and we are going to iterate through this nodes, and if it is not visited, then we are going to call DFS function. So yes, once we call DFS function, we are finally returning our result. So let's spend some time in writing our DFS function now. So here I'm gonna get the same ID of the node. So for the first time, the ID and low is going to be the same for every node. So we are going to iterate the time, which is nothing but the order where we visit the node. So we are going to assign that ID and low both same for the nodes every time. So we are going to iterate through the given node. So here G of U will have the list of nodes it has connected with. So we are going to take each connected node. Then we are checking if it is the same node. Then we are simply skipping the steps. If not, we are going to check if it is not already visited. So if it is not visited, so we are going to compare every time whether the low value is greater than the neighboring ID value. Then in that case, there is a critical connection. So we are going to add that edges to our result. And every time once the iteration is completed, we are going to assign low of U is equal to minimum value in that cycle. So let's run and try. So yes, let's submit. So yes, the solution is accepted and runs in 89 millisecond, which is 86% faster than other solutions. So thanks for watching the video. If you like the video, hit like, subscribe, and let me know in comments. Thank you.